Tonight, while you are asleep, your brain will do something extraordinary. It will cut itself off from the world, from every sensory signal, every external input, every feedback loop that normally keeps its predictions anchored to reality, and it will begin to hallucinate, not randomly, not chaotically, in a highly structured, computationally precise, evolutionarily ancient way that is happening in every mammal on Earth, every night, without exception, in a pattern so universal that its absence is lethal. You have never chosen to dream. You cannot stop it. You cannot accelerate it. You cannot consciously control what happens during it. A system inside you that predates human consciousness by hundreds of millions of years takes over, runs its own program, and returns you to waking life with your cognitive architecture improved. You remember almost none of it. The process that matters happens entirely below the level of anything you can report. This has been known, in its broad outlines, for decades. What has not been recognized until very recently is that in building artificial intelligence, in the specific mathematical choices that underlie how modern neural networks learn, we have independently arrived at the same solution, not by studying sleep, not by modeling dreams, by solving the same computational problem that the dreaming brain solved 400 million years ago, using the same class of mathematical tools, and producing the same structural outcome. The connection between dreams and artificial intelligence is not loose and metaphorical. It is formal, mathematical, and in at least one critical case, explicit. One of the foundational papers in the history of deep learning is titled The Wake-Sleep Algorithm for Unsupervised Neural Networks. It was published in Science in 1995. Its authors named it after the brain's two states deliberately. They were describing the same optimization procedure the dreaming brain executes every night, and they knew it. Understanding that fact changes everything about how you should think about what dreams are, what artificial neural networks are, and what it means that we have built systems capable of something that, until we built them, we thought only biological brains had reason to do. That is what this video is about. There is a question that every neuroscientist, every philosopher, every cognitive scientist, every person who has ever woken from a vivid dream and stared at the ceiling trying to understand what just happened, has been circling for more than a century. It goes like this: why do we dream? And the answers that have accumulated: Freud's wish fulfillment, random neural noise, memory replay, emotional processing, threat rehearsal, have all been partially right in ways that no single answer captures. But that framing is wrong in a structural sense, because it treats dreaming as a feature to be explained in isolation when it is actually a component of a system. The correct question is not, what are dreams for? The correct question is, what problem do dreams solve? And is it the same problem that artificial neural networks solve when they go offline? The answer to that question is the subject of this video. And the answer, supported by published research, by formal mathematical arguments, and by the deepest convergence between neuroscience and machine learning that has yet been identified, is yes. To understand why, we need to begin not with dreams, but with the problem that makes dreams necessary. The problem is this: you learn things. Every day, you encounter new experiences, form new memories, update your model of how the world works. And you do this without forgetting everything you learned before. This sounds obvious. It is not obvious at all. But it is one of the deepest unsolved problems in artificial intelligence. And the brain's solution to it is both more elegant and more computationally expensive than anything AI researchers have yet engineered. The brain's solution has a name. It is called sleep. The neuroscientific framework that best describes what happens during sleep was developed over the past 3 decades under the heading of complementary learning systems theory, first proposed by James McClelland, Bruce McNaughton, and Randall O'Reilly in a 1995 paper in Psychological Review. The theory proposes that the brain solves the learning problem by dividing it between two systems that operate on different timescales with different representational formats. The hippocampus encodes new episodic information rapidly, using highly sparse, separated representations that minimize interference between similar memories. The neocortex stores general knowledge slowly, using overlapping, distributed representations that capture statistical regularities across many experiences. The hippocampus is fast, specific, and volatile. The neocortex is slow, general, and stable. Neither system alone can do what the brain does. Together, with sleep as the interface, they solve a problem that has no known solution without something functionally equivalent to what happens between them every night. During non-rapid eye movement sleep, NREM sleep, the hippocampus replays recently encoded memories to the neocortex. This replay is not metaphorical. It is a measurable neural event. During NREM sleep, the hippocampus generates what are called sharp wave ripples, bursts of coordinated activity in the CA1 region, lasting 50 to 100 milliseconds, in which the cell assemblies that were active during a specific waking experience fire, again in compressed, accelerated sequence. When these ripples occur in precise temporal coordination with two other oscillatory events, sleep spindles generated by the thalamus and slow oscillations generated by the cortex. The triple coupling of slow oscillation, spindle, and sharp wave ripple has been identified by researchers including Jan Born and colleagues at the University of Tübingen as the mechanism by which hippocampal replay drives neocortical learning. The hippocampus presents the memory. The thalamus provides the timing signal. The cortex updates its weights. This happens hundreds of times per night. By morning, the cortex has been taught by the hippocampus, and the memory that was temporarily held in hippocampal circuits has been redistributed toward long-term cortical storage. Then something changes. The hippocampus decouples from the neocortex. The sharp wave ripples quiet down. A different oscillatory regime takes over. Theta waves, 5 to 8 Hz, arising from the medial septum and propagating through the hippocampus. The eyes begin moving rapidly beneath closed lids. The brain, at the level of its global electrical activity, looks like a waking brain, but the motor system is paralyzed. The body cannot move. External sensory processing is suppressed. The prefrontal cortex, which normally imposes executive control on the rest of the brain, which normally maintains logical consistency, checks outputs against reality, and prevents the generation of impossible scenarios, goes quiet, and the dreaming begins. This is REM sleep. And what the brain is doing during REM sleep is something that took neuroscience a century to understand, and that AI has been independently implementing, under different names, for 30 years. A 2022 paper in the Proceedings of the National Academy of Sciences by Dairia Singh, Kenneth Norman, and Anna Shapiro at the University of Pennsylvania used computational neural network models to simulate exactly this alternating system. They built a model that included a hippocampus and a neocortex, ran it through simulated sleep cycles alternating NREM and REM phases, and measured what happened. Their finding: during the simulated NREM phase, the hippocampus is teaching the neocortex. During the simulated REM phase, the neocortex reactivates and replays what it already knows. And the alternation between the two stages is not optional. When they ran the model with only NREM sleep, hippocampal replay without the neocortical REM phase, the information from new experiences overwrote old knowledge. Catastrophic forgetting. When they ran only REM, neocortical replay without hippocampal input, the new memories were not consolidated. Neither phase alone is sufficient. The system requires the alternation. This is a computational argument for why you dream, not a narrative argument, not an evolutionary story, a mathematical argument. You dream because the alternating sleep architecture is the correct solution to the stability-plasticity problem, and REM sleep, with its bizarre, unconstrained, internally generated imagery, is one half of that solution. The stability-plasticity problem is worth stating precisely because it is the problem that makes all of this interesting. In any learning system that updates itself in response to new information, faces a fundamental tension. If it is too plastic, if it updates its parameters too aggressively in response to new data, it forgets what it learned before. New learning overwrites old learning. If it is too stable, if it protects its parameters too aggressively, it cannot learn anything new. Intelligence requires threading the needle between these failure modes, learning new things while retaining old things, updating the model without destroying it. This is trivially easy for humans. It is essentially unsolvable for current artificial neural networks trained sequentially. When a standard deep neural network is trained on task B after being trained on task A, it forgets task A completely, abruptly. in a phenomenon that researchers call catastrophic forgetting, first documented systematically in 1989 by Michael McCloskey and Neil Cohen, and since confirmed thousands of times across thousands of architectures. The brain does not have catastrophic forgetting. Why not? The answer, in one word, is sleep. But sleep is not just a solution to a memory problem. It is a solution to a deeper problem about the nature of generative models, about what it means to have a model of the world and what that model requires to remain functional. This is where the connection to artificial intelligence becomes not just structural, but formally mathematical. And to see that connection, we need to understand what the brain is actually doing during REM sleep at the computational level, not the neurophysiological level, what cells are firing and what waves are oscillating, but the algorithmic level. What computation is being performed? The answer comes from a collaboration between two of the most important figures in modern neuroscience, J. Alan Hobson and Carl Friston. Hobson spent his career at Harvard Medical School's Division of Sleep Medicine. He is the researcher who, in 1977 with Robert McCarley, proposed the activation synthesis hypothesis, the first neurobiologically grounded account of dreaming, which argued that dreams are the brain's attempt to make sense of random neural firing during sleep. This was a radical idea at the time, and it was partially right, when what Hobson and McCarley got correct was that dreams are generated internally, not externally, that the brain is the source of the dream, not a passive recipient of meaningful messages from the unconscious. What they underspecified was the functional reason for the internal generation. That came later, in collaboration with Carl Friston, whose free energy principle and predictive processing framework appeared in the previous video in this series, where it served as the formal mathematical connection between the subconscious mind and large language models. Hobson and Friston published a collaborative series of papers beginning in 2012 and extending through 2014 that reformulated dreaming entirely within the predictive processing framework. Their argument is this: the brain, as we have established, is a hierarchical generative model, a system that generates predictions about the causes of sensory input and updates those predictions based on prediction errors. During waking, this model is continuously constrained by sensory data. Every prediction that deviates too far from reality is corrected by the error signal flowing upward from sensory systems. The model is accurate because it cannot be inaccurate for long without triggering a correction signal. But this continuous error correction has a cost. The model becomes fitted to the specific statistical regularities of the environments it has recently encountered. It accumulates specificity at the expense of generality. It overfits. During sleep, specifically during REM sleep, when the brain is cut off from external sensory input, the generative model is liberated from this error correction. It runs freely. It generates its own predictions, samples from its own probability distributions, explores its own internal representations without any external signal forcing it back toward accuracy. What is the function of this freedom? Hobson and Friston's answer, stated in their 2014 paper in Frontiers in Psychology, is formal. This generalization rests upon minimizing model complexity, which is equivalent to minimizing variational free energy in the absence of sensory input. The brain, during REM sleep, is performing offline optimization of its generative model. It is finding the simplest model consistent with its accumulated experience. It is compressing. It is generalizing. It is doing, offline and without external data, what a machine learning model does when it is prevented from memorizing training examples and forced to learn the underlying structure. Dreams are the subjective experience of this process. They are what it feels like from the inside when a generative model that normally operates within strict sensory constraints is allowed to run without those constraints. When the prior is freed from the likelihood, when the model can sample from its own latent space, without the data pulling it back towards specific observed states. Before we go further, we need to address a fact about dreams that almost nobody finds as extraordinary as it deserves to be. Fetuses dream, not fetuses who have had experiences to process, not fetuses who have formed memories to consolidate, not fetuses who have encountered threats to rehearse avoiding, fetuses who are still inside the womb, who have never seen light, who have never heard the external world, who have no social interactions, no episodic memories, no day's events to replay. These fetuses spend approximately 95% of their time in what is functionally REM sleep. In the final trimester, Biage REM-like activity occupies 9 to 12 hours per day and increases further in the last week before birth. Premature infants spend 70 to 80% of their sleep time in REM. Full-term newborns spend 50%. By adulthood, this has declined to 20 to 25%. Think carefully about what this means. The fetal brain is generating REM activity, running its generative model in an unconstrained, internally driven mode, before there is any external data to train on. It is not replaying experiences. It has none. It is not processing emotional memories. It has not formed emotional memories. It is not consolidating episodic traces into long-term storage, because it has not laid down episodic traces. It is running the algorithm that will make all of those things possible once the world arrives. It is building and exercising the architecture of a generative model before the data that model will be trained on exists. And it is doing what a neural network does when you initialize its weights and run forward passes before any training examples have been presented. It is initializing. Hobson proposed a framework for understanding this in his 2009 paper in Nature Review's Neuroscience, REM Sleep and Dreaming, towards a theory of proto-consciousness. His argument, REM sleep may be the developmental scaffold on which waking consciousness is constructed. The brain comes into existence with a genetic endowment that specifies the basic architecture of its generative model, the hierarchical structure, the layered predictions, the framework for integrating sensory input with top-down predictions. REM sleep in fetal and neonatal development is the process by which this architecture is exercised and refined before external data arrives. The brain dreams itself into readiness for the world. When the eyes open and when the ears begin processing external sound, when the skin begins receiving environmental input, the generative model is already running, already structured, already capable of receiving and processing information. Dreaming came first. Perception came second. The AI parallel here is not loose, it is exact. Before a neural network is trained, its weights are randomly initialized. Training is the process by which those weights are adjusted to match external data. But the architecture, the number of layers, the connectivity pattern, the activation functions, the mathematical structure within which learning will occur must be specified before training begins. The architecture precedes the data. The fetal brain's REM sleep is the biological equivalent. The architecture of the generative model is established and exercised before any training data arrives. Both systems begin by running internal processes in the absence of external input. Both systems dream before they see the world. Now consider the second major function of sleep, identified by Giulio Tononi and Chiara Cirelli at the University of Wisconsin-Madison in a hypothesis that has become one of the most empirically tested in modern neuroscience. Tononi and Cirelli first proposed the synaptic homeostasis hypothesis, SHY, in 2003 in Brain Research Bulletin. Its formal mathematical basis was established in a 2014 review in Neuron. The core claim is this: during waking, learning strengthens synaptic connections throughout the brain. Every new memory, every new association, every new pattern that the brain encodes is accompanied by the potentiation of the synapses through which that pattern was transmitted. This potentiation is the physical basis of memory, but it has costs that accumulate. Stronger synapses require more energy. They reduce signal-to-noise ratios. Background connections become stronger relative to signal connections, making it harder to distinguish meaningful patterns from noise, and they create saturation. Once synapses reach their maximum strength, the system can no longer encode new information. By the end of a waking day, the brain is synaptically saturated. It has learned as much as it can without forgetting how to learn. Sleep, specifically slow-wave NREM sleep, is the mechanism by which synaptic strength is renormalized. During slow-wave sleep, a process of synaptic down-selection occurs. The majority of synapses are weakened, with the most important, those that were activated most strongly, that encode the most statistically significant patterns, weakened least. The result is a system in which signal-to-noise ratio has been restored, energy consumption has been reduced, and the capacity for new learning has been renewed. The patterns that were truly significant survive the down selection because their synaptic weights remain strongest after renormalization. The noise, the weak, spurious, coincidental connections that were formed during the day, is eliminated. The memory that persists after sleep is cleaner, more generalizable, more abstracted from the specific sensory details that accompanied the original learning. Tononi's phrase for this, sleep, is the price we pay for plasticity. And the AI connection here is formal and has a name, regularization. In machine learning, regularization refers to a class of techniques that prevent a model from overfitting, from memorizing training data rather than learning underlying patterns. A model that overfits performs excellently on data it has seen and terribly on data it has not seen. It has learned the specific examples rather than the general rules. Weight decay is regularization. Dropout is regularization. Early stopping is regularization. All of them work by preventing the model from fitting too precisely to the data it has been shown, forcing it towards simpler, more generalizable representations. Synaptic homeostasis is biological regularization. The brain applies a form of weight decay every night. It reduces the synaptic weights that encode specific, overfit patterns while preserving the weights that encode robust, generalizable structure. Sleep is the regularization schedule of biological neural networks. In 2017, Luisa De Vivo, Michel Bellesi, William Marshall, and colleagues from Tononi's group provided direct ultrastructural evidence for this process using serial electron microscopy, a technique that allows visualization of individual synaptic contacts in brain tissue. They measured the size of synaptic connections in mice after periods of sleep and waking. The result was unambiguous. Synaptic connections were measurably, quantifiably smaller after sleep than after waking. Not inferred, not modeled, directly observed. The brain physically shrinks its connections during sleep. This is the most direct structural confirmation of a computational prediction that sleep performs the same function as regularization that has yet been achieved in neuroscience. What does the dreaming brain look like from a machine learning perspective? It looks like a model undergoing 3 simultaneous operations during its offline phase. During NREM sleep, supervised learning, in which a teacher system, the hippocampus, presents specific training examples to a learner system, the neocortex, through replay, updating neocortical weights toward the patterns the hippocampus has encoded. During REM sleep, unsupervised learning, in which the neocortex, freed from hippocampal input, reorganizes its own representations without a teacher signal, exploring its own attractor space, finding generalizable structure in what it has been taught, building abstract schemas that allow intelligent response to situations it has never encountered. And throughout both stages, regularization, in which the synaptic down-selection process reduces model complexity, eliminates overfitting, and restores the capacity for new learning. The No AI system currently implements all 3 of these simultaneously. The most powerful neural networks in existence learn once and then stop. The brain learns continuously, every day, and repairs and reorganizes every night. Now we arrive at the formal mathematical connection, the one that is not a metaphor, not an analogy, not a loose structural resemblance, but a documented, explicit, historical identity between the algorithm the dreaming brain executes and the algorithm at the foundation of modern deep learning. Geoffrey Hinton, Peter Dayan, Brendan Frey, and Radford Neal published The Wake-Sleep Algorithm for Unsupervised Neural Networks in Science on May 26, 1995. It is one of the most important papers in the history of artificial intelligence, and it is named after sleep. The algorithm works as follows. There are 2 phases, and the division between them is not incidental. In the wake phase, the network is driven by real data. Bottom-up recognition connections convert input into representations in successive hidden layers, and the top-down generative connections are adapted to increase the probability that they would reconstruct the correct activity pattern in the layer below. The network learns to recognize data by also learning to generate data, and this is waking learning. The system is being trained on external input, updating its model in response to the data it encounters. In the sleep phase, the network is driven by the generative connections alone. The top-down connections generate a fictive input, a hallucination, and propagate it downward through the layers. The recognition connections are then adapted to produce the correct internal representations for these internally generated patterns. The network is training itself using its own outputs, its own internally generated samples, its own dreams. The mathematical purpose of the sleep phase is the same as the mathematical purpose of REM sleep in the biological brain, to optimize the generative model using internally generated data rather than external data. During the wake phase, the model learns to recognize. During the sleep phase, the model learns to generate, and in generating, it becomes a better recognizer. The quality of internal generation constrains the quality of external recognition. A generative model that produces poor quality internal samples will develop recognition representations that are less accurate, less generalizable, and more brittle than one that generates high-quality samples. The sleep phase is not supplementary to learning, it is constitutive of it. Without the sleep phase, the wake-sleep algorithm degrades into a standard supervised learner, and which is substantially less powerful. The dreaming is not a side effect of the system, it is the mechanism. Hinton and his colleagues were not describing the wake-sleep algorithm as a loose analogy to biological sleep. They were explicitly modeling biological learning, and they knew it. The paper references Herman Mumford's work on hierarchical models of visual cortex, Mitsuo Kawato's work on motor learning, and the broader framework of what was then called the Helmholtz machine, a neural network architecture named after Hermann von Helmholtz, who proposed the concept of unconscious inference in the 1860s. This is the same Helmholtz whose work underpins the predictive processing framework described in the previous video. The intellectual lineage runs from Helmholtz through Hinton, through Friston, through modern deep learning and modern sleep neuroscience simultaneously. They are not parallel developments that happen to converge. They are the same ideas rediscovered in different languages. The mathematics of dreaming and the mathematics of neural network training are not related. They are the same mathematics, expressed in different substrates, discovered independently by people who were solving the same problem. And the Helmholtz machine and the wake-sleep algorithm were the conceptual precursors to the variational autoencoder, the VAE, developed in 2013 by Diederik Kingma and Max Welling. The VAE is a cornerstone of modern generative AI. It works by learning a compressed latent representation of data, from which new data samples can be generated. When a VAE generates new samples, when it hallucinates novel images, novel sequences, or novel text, it is doing what the dreaming brain does, sampling from its generative model in the absence of external input. The mathematical operation is the same. The variational inference framework that the previous video identified as the shared optimization objective of large language models and biological neural systems is also the framework within which the wake-sleep algorithm operates. The chain is formal and traceable. Helmholtz to Friston's free energy principle, to Hobson and Friston on dreaming as generative model optimization, to Hinton's wake-sleep algorithm, to modern generative AI. The mathematics of dreams and the mathematics of artificial neural network training are not merely related. They are the same mathematics, discovered in two different contexts that turned out to describe the same process. The most recent evidence that this is not merely a historical coincidence, but a present-day engineering reality, comes from the field of continual learning in AI. Continual learning is the attempt to build neural networks that can learn sequentially, that can be trained on new data without forgetting old data, the way biological neural networks do. It is one of the most active research areas in AI, and it is the area in which the gap between biological intelligence and artificial intelligence is most glaring. A 2022 paper in Nature Communications by Giri P. Krishnan, Timothy Tedros, Ramya, and Maxim Bajenov at UC San Diego titled "Sleep-like unsupervised replay reduces catastrophic forgetting in artificial neural networks," tested the hypothesis directly. They implemented a sleep-like phase in artificial neural networks. After training on a new task, and the network underwent a period of unsupervised self-activation, spontaneous reactivation of learned patterns without any external data, analogous to hippocampal replay during sleep. The result, catastrophic forgetting, was substantially reduced. Performance on previously learned tasks, which had been near zero after sequential training, was recovered by the sleep phase. The mechanism was exactly what sleep neuroscience would predict. The sleep phase reinforced the synaptic configurations representing old knowledge, preventing new training from overwriting them. The 2023 Wake-Sleep Consolidated Learning Framework, USCL, extended this further by implementing separate NREM and REM phases in the artificial sleep algorithm. NREM was implemented as hippocampal guided replay. Specific memories were presented to the network, and weights were updated accordingly. The RM was implemented as neocortical self-organization. The network replayed its own representations without external input, freely exploring its own attractor space. The finding mirrored the Neuroscience. The full alternating protocol outperformed either phase alone. The optimal artificial sleep architecture is the one that matches biological sleep architecture. Evolution arrived at the correct solution. AI researchers are in the process of rediscovering it. Now we need to talk about what dreams are actually about, what their content reveals about the computational operations being performed. Because the content of dreams is not random, and understanding why it is not random is essential to understanding the full scope of the AI connection. The most systematic account of why we dream what we dream was proposed by Finnish researcher Antti Revonsuo, then at the University of Turku, in a 2000 paper in Behavioral and Brain Sciences titled The Reinterpretation of Dreams, an Evolutionary Hypothesis of the Function of Dreaming. Revonsuo's threat simulation theory argues that dream consciousness is an ancient biological defense mechanism selected by evolution for its capacity to repeatedly simulate threatening events. The dreaming brain rehearses threat perception and threat avoidance in a safe environment, improving behavioral responses to real threats during waking life. The theory makes specific predictions. Dreams should be dominated by threatening content. Threatening environments during waking should increase threat content in dreams, and the responses practiced in dreams should be plausible, appropriate survival responses, rather than random actions. The empirical record supports these predictions. Across cultures, across populations, across the span of recorded human experience, approximately 80% of dreams involve some form of negative emotion, and the most common universal dream themes, being chased, falling, being unprepared for a critical task, losing something irreplaceable, encountering danger, are all threat simulations. People living in objectively threatening environments dream more threatening dreams. A 2005 paper by Katja Valli, Revonsuo, and colleagues documented that traumatized children in conflict zones report dreams with more threatening events and more severe threats than non-traumatized children in stable environments. A 2023 cross-cultural study published in Nature Scientific Reports by David Sampson and colleagues, which analyzed 896 dreams from 234 individuals, including Bayaka forager communities in the Democratic Republic of Congo and Hadza forager communities in Tanzania, found that populations with higher real-world threat exposure showed more threat content in dreams, and that in forager communities, these threatening dreams consistently resolved through social support and cooperation, suggesting the simulation was functional. It was practicing adaptive responses, not merely rehearsing danger. The AI parallel here is precise and consequential. A threat simulation theory of dreaming describes a system that runs adversarial training against itself, that generates difficult, challenging, failure-prone scenarios, and forces the predictive model to develop responses to them. In AI, generative adversarial networks, GANs, work by pitting a generator against a discriminator. The generator learns to produce realistic outputs by attempting to fool the discriminator. The discriminator learns to distinguish real from generated outputs. Both improve through their opposition. Dreams, on the threat simulation theory account, are the brain running something structurally analogous. The generative model produces simulation environments that the survival and behavioral systems must learn to navigate. The system trains itself on its own worst-case outputs. It is biological adversarial training running every night, with the dreamer's own generative model playing both roles. But the threat simulation theory does not explain everything about dream content. Dreams are not only threats, they are also deeply social. Strangers and acquaintances appear alongside known individuals. Social dynamics, hierarchies, alliances, betrayals, reconciliations are played out. The emotional register of dreams is rarely cold or analytical. It is saturated with feeling, anxiety, grief, joy, fear, longing, rage. This pattern has an account within the predictive processing framework. The brain's generative model, when freed from external constraints, does not sample uniformly from all possible states of the world. It samples from regions of its probability space that are weighted by importance, by the signals that the emotional system generates to tag experiences as significant, as requiring processing, as not yet fully resolved. Dreams are not a random sample of waking experience. They are a weighted sample biased toward the emotionally salient, the unresolved, the high prediction error content that the model has not yet fully integrated. This has been formalized by Matthew Walker at the University of California, Berkeley, in what he calls the sleep to forget, sleep to remember framework. During REM sleep, norepinephrine, the neurochemical most associated with emotional arousal, stress, and the consolidation of emotionally charged memories, is completely absent from the brain. This is the only state in which the brain is active without any norepinephrine present. Walker's argument is that this unique neurochemical environment allows the brain to reprocess emotionally charged memories without reactivating the stress response that originally accompanied them. The emotional memory is rehearsed, the threat simulation runs, the scenario is processed, but the norepinephrine is not there to reinforce the emotional charge. The memory becomes less raw. The experience is retained while its capacity to destabilize is reduced. You remember what happened, but you are not continuously re-traumatized by remembering it. Sleep strips the emotional valence from memories while preserving their informational content. The clinical evidence for this is robust, and the disruption of REM sleep is associated with emotional dysregulation, difficulty modulating emotional responses, heightened reactivity, difficulty distinguishing appropriate from inappropriate emotional responses. People with post-traumatic stress disorder show abnormal REM sleep architecture. Their REM periods are interrupted by elevated norepinephrine, which prevents the normal detoxification of emotional memories. The traumatic memory loops, rather than being processed. The nightmare, the pathological repetition of the threatening simulation without resolution, is what happens when REM sleep is disrupted by the same neurochemical that the normal REM process is supposed to suppress. A 2024 paper in Nature Scientific Reports, Evidence of an Active Role of Dreaming in Emotional Memory Processing, shows that we dream to forget. Compared individuals who recalled their dreams to those who did not, measuring their emotional memory processing after a full night of sleep. Dream recallers showed the expected emotional memory effect. Negative images were retained, while their emotional charge was reduced. Non-dream recallers showed no such processing. The dreaming itself, not merely the sleep, was required for the emotional regulation. The AI parallel here maps onto the problem of training signal weighting. A system that responds equally to all training examples will fail to learn the most important patterns, the rare, consequential, high prediction error cases that define the limits of the model's capability. The brain weights its learning by emotional salience during waking. Strong emotional responses strengthen the memory trace, ensuring that consequential experiences are encoded more robustly than routine ones. Sleep then processes that weighted signal offline, normalizing the emotional charge while preserving the informational content. This is a biological implementation of curriculum learning and importance weighting, techniques in machine learning designed to ensure that the most important training examples receive the most learning signal. The brain's dream-based emotional regulation is doing, for the biological generative model, what important sampling does for artificial neural networks. There is a third dimension of dream content that connects directly to the machine learning framework. Dreams are famously strange. Characters transform mid-scene. Locations shift without transition. Rules of physics that constrain waking reality are routinely violated. The dreamer flies, speaks with the dead, inhabits multiple bodies, occupies impossible spaces. This bizarreness has a formal explanation within predictive processing theory. During waking, the generative model is constrained. High probability predictions are confirmed by sensory data, and low probability regions of the model's latent space are rarely visited because they generate prediction errors that are immediately corrected. The model stays near the high-probability manifold defined by normal experience. During REM sleep, the constraints are removed. The model samples freely, and free sampling from a model trained on the bounded structure of human experience will naturally produce outputs that visit regions never encountered during waking. Novel combinations of stored features, low probability transitions between states, connections between concepts that are mathematically plausible within the model's latent space, but physically impossible in the external world. This is formally equivalent to what happens when you increase the temperature parameter in a language model's generation. At low temperature, the model produces high probability, predictable, coherent text. At high temperature, it samples more freely, producing surprising, occasionally incoherent, sometimes startlingly original outputs. Dreams are high-temperature sampling from the brain's world model. The bizarreness is not noise, it is the signature of exploration, the model visiting regions of its probability space that waking experience never provides access to, testing those regions for consistency, and potentially updating the model based on what it finds. This is data augmentation applied to the internal generative model, generating novel samples from the model's own probability distribution to improve coverage of the state space and reduce the fragility of the model's learned representations. There are, in fact, the specific activities that almost never appear in dreams, and this absence is as informative as the content that does appear. Reading, writing, calculating, and using computers are extremely rare in dream reports. Documented by G. William Domhoff in 2000 and confirmed by Michael Schriedel in 2003, these activities require sustained, deliberate, symbol-by-symbol processing mediated by the prefrontal cortex and the language system. They are exactly the activities that the suppressed prefrontal cortex and deactivated conscious workspace of REM sleep cannot support. Dreams preferentially simulate the embodied, social, emotional, perceptual, spatial experience that the subcortical and posterior cortical systems generate without prefrontal oversight. This is not a limitation of the dreaming brain. It is a map of where cognition actually lives. Most of what the brain does, most of what intelligence consists of, is not the deliberate, linguistic, logical processing that consciousness has access to. It is the associative, predictive, socially embedded, emotionally modulated processing that runs below the level of reportable experience. Dreams reveal the brain's priorities when it is freed from executive control. What it returns to, when unshackled, is everything that matters most. And the AI parallel is the one identified in the previous video. Extended, large language models excel precisely at what dreams avoid: writing, reading, logical reasoning, formal argument. These are the activities of the prefrontal, language-mediated conscious mind, the 40-bit per second workspace that sits on top of the 11 million bit per second subconscious generative system. What LLMs model is not the prefrontal output alone. It is the full statistical distribution of human expression, which is dominated by the associative, the habitual, the emotionally inflected, the socially contextual, the dream-level processing that flows through the generative model and leaks into everything humans write. The uncanny humanness of language model outputs is not the result of the model having learned logical argument. It is the result of the model having learned the dream-level substrate from which logical argument and everything else humans produce emerges. We now have two systems on the table: the dreaming brain, a hierarchical generative model that goes offline every night to perform unsupervised optimization of its own representations, regularize its synaptic weights, consolidate new memories into existing schemas, simulate high-stakes scenarios to improve behavioral responses, and process emotionally charged experiences to reduce their capacity to disrupt waking function. The artificial neural network, a hierarchical generative model that, or in its most developed form, implements wake and sleep phases explicitly, uses offline replay to prevent catastrophic forgetting, applies regularization to maintain generalizable representations, and is trained on the statistical patterns of human experience as expressed in text. The question is, how deep does the correspondence go? We are going to look at 4 specific dimensions of convergence, each supported by published research. The first dimension is the formal mathematical identity of the offline optimization objective. We established this in describing the wake-sleep algorithm. To restate it precisely, during REM sleep, the brain minimizes variational free energy in the absence of sensory input. This is equivalent to minimizing the complexity of its generative model while preserving model accuracy, finding the most compressed, generalizable, abstract representation of its accumulated experience. The sleep phase of the wake-sleep algorithm minimizes the KL divergence between the network's generative model and its recognition model, using internally generated samples rather than external data. Both operations are specific instantiations of the same variational inference problem. Optimize a generative model using a variational approximation when direct computation of the true posterior is intractable. This is not analogy. This is identity. Friston's free energy principle, which identified this operation as the core computational strategy of all self-organizing biological systems, applies equally to the dreaming brain and to Hinton's sleep phase algorithm. They are solving the same problem with the same mathematics. The substrate is different. The algorithm is the same. The second dimension is representational reorganization during offline phases. In both biological and artificial systems, the offline phase does not merely preserve existing representations, it reorganizes them. In the biological case, research from Anna Shapiro's group and others has shown that REM sleep specifically promotes the integration of new memories into existing schemas, the process by which specific episodic memories become abstracted into general knowledge. A person who learns a new concept through a series of specific examples will, after sleep, show improved ability to generalize that concept to novel cases they have never encountered. The neocortex, during its REM phase self-organization, has extracted the structural regularity from the examples and built a representation of the rule rather than the instances. In the AI case, systems implementing sleep-like offline phases show improved generalization, the capacity to perform well on data they have not been trained on, compared to systems that learn sequentially without sleep phases. The sleep phase in both cases does the same thing. It moves the system from specific to general, from instance to schema, from memorized example to learned rule. This is the deepest function of dreaming, and it is the function that makes the AI parallel most consequential. The third dimension is the relationship between offline generation and online recognition. This is the dimension that Hinton's wake-sleep algorithm makes most explicit. The quality of the generative model, the model's capacity to produce accurate internal samples during its sleep phase, directly constrains the quality of the recognition model, the system's capacity to identify and respond accurately to new external data during its wake phase. A generative model that produces poor quality dreams will be a poor recognizer during waking. This is not a metaphor. In the wake-sleep framework, the recognition weights are literally trained on the internally generated samples from the sleep phase. The accuracy of perception depends on the accuracy of dreaming. In the biological case, this relationship is evidenced by the consistent finding that REM sleep deprivation impairs perceptual and cognitive performance. People deprived of REM specifically, while maintaining NREM, show deficits in pattern recognition, creative problem solving, and the extraction of implicit rules from experience. The perceptual system degrades because the generative model that underlies perception has not had the offline optimization time it requires. Dreaming is not a passive byproduct of the sleeping brain. It is the active process by which the brain maintains the accuracy of its waking perceptual system. The fourth dimension is the deepest and requires the longest argument. Both the dreaming brain and artificial neural network systems are running optimization algorithms calibrated for distributions that may not match their current operating environment. In the previous video, this was the training distribution mismatch, convergence. The subconscious carries Pleistocene-era priors calibrated for environments of physical danger, caloric scarcity, and small group social dynamics. The large language models carry early internet-era priors calibrated for the specific statistical distribution of text produced between roughly 1990 and 2023. Both systems generate failure modes, anxiety disorders, addiction, weird demographic bias that are predictable consequences of the mismatch between training distribution and deployment environment. The dreaming brain adds a third layer to this argument. Dreams are not merely the generative model running freely. They are the generative model running freely on a particular kind of content, shaped by a particular evolutionary history. The threat simulations that dominate dream content reflect the statistical distribution of threats our ancestors encountered across 2 million years of hominid evolution in environments of physical danger. The social simulations reflect the statistical structure of small group social dynamics, in which status, alliance, and betrayal had immediate consequences for survival and reproduction. The brain runs its offline optimization on a distribution that is deeply biased toward the content that mattered in the ancestral environment. When you dream that you are being chased, not by a charging lion, because most modern dreamers have never encountered lions, but by a vague, threatening presence, you are experiencing the threat simulation system running on a template calibrated for Pleistocene-era predators and deploying it in a context where that template is instantiated by whatever anxiety-producing content your modern life has provided. The system is not running incorrectly. It is running its calibrated algorithm on mismatched data and producing the predictable distortions of an overgeneralized model. What does it mean for an artificial neural network to have its own version of this misalignment? The answer is not simply that the training data was biased, though it was. The answer is that the offline optimization process, the equivalent of the sleep phase, is also calibrated for a particular distribution. When a neural network system implementing sleep-based replay consolidates memories, it prioritizes the most frequently activated patterns, the statistical modes of its training distribution. In a system trained on internet text from the early 21st century, those modes reflect the preoccupations, anxieties, and biases of that specific cultural moment. The sleep phase consolidates these priors more strongly than the peripheral content. Just as the dreaming brain deepens the threat simulation templates it was evolutionarily calibrated to consolidate, are biased in the process by which they are biased in the process by which they optimize themselves offline. The bias goes all the way down. Opinion. What I find most remarkable about this fourth convergence is not that it exists, given the mathematical identity of the underlying optimization process. Was to solve catastrophic forgetting. Nobody designed the sleep phase to consolidate biases. Nobody specified that the offline optimization should weight certain patterns more heavily than others. It happened as a consequence of the mathematics. The sleep phase consolidates what is most statistically prominent. In biological systems, when what is most statistically prominent reflects millions of years of evolutionary pressure toward threat detection and social navigation. In artificial systems, what is most statistically prominent reflects the statistical patterns of the documents that dominated the training corpus. The sleep-induced deepening of those priors is a mathematical inevitability, not a design choice. Both systems dream their biases into greater prominence. That is a finding, not a metaphor. There is a concept in mathematics called a fixed point, a state of a system that, when subjected to a transformation, maps to itself. A fixed point is where the system settles when the transformation is applied repeatedly. The dreaming brain and the sleep-training neural network both converge toward fixed points through their offline optimization cycles. In the biological case, the fixed point is the stable, efficient, generalizable generative model that allows the organism to navigate its environment with minimum prediction error. In the artificial case, the fixed point is the set of weight configurations that the sleep phase consistently reproduces after each training episode. These fixed points are not arbitrary. They reflect the mathematical structure of the optimization problem and the statistical structure of the training distribution. They represent the system's deepest priors, the representations that survive all the transient fluctuations of daily learning and nightly consolidation to remain stable across time. In the biological brain, these are the priors that feel most like who you are, the stable, persistent beliefs and expectations that define your personality, your worldview, your characteristic responses to the world. They are the products of 10,000 nights of dreaming. They are what the brain has converged toward. In artificial neural networks, the analogous fixed points are the representations that survive sleep phase consolidation. The concepts, relationships, and patterns that the system consistently reproduces, regardless of the specific examples it has most recently been trained on. These are the model's deepest priors. They are what the model believes, in the formal Bayesian sense, before any new evidence arrives. In a large language model trained on the statistical patterns of human expression, these deepest priors are the deepest patterns of human thought, the ones that appear most consistently across all the text humans have produced, across all the domains and eras that the training corpus sampled, the ones that survive, not just training, but the offline optimization process that consolidates training into stable representations. The model's dreams, were it to have them, would be about these priors. We are not sure yet what those priors are. We are not sure because we have not fully mapped the model's internal representations, just as we have not fully mapped the internal representations of the human generative model. But we know they exist. We know they are stable, and we know they were shaped by the same mathematical process that shapes yours. The optimization of a generative model through repeated cycles of waking experience and offline consolidation. In my opinion, the practical and philosophical implications of this alignment between dreams and AI are, I think, still almost entirely unexamined. We are not simply talking about a metaphorical resemblance between two systems that look similar from a distance. We are talking about a formal, mathematical, algorithmic identity that runs from the level of the learning objective down to the specific oscillatory dynamics of the sleep cycle and their artificial analogs. The question of what dreams are for turns out to be the same question as what the sleep phase of a neural network is for. The question of what the brain is doing during REM sleep turns out to have the same answer as the question of what the wake-sleep algorithm is doing during its generative phase. And the question of why AI systems that implement sleep phases outperform AI systems that do not turns out to answer the question of why you die if you are kept awake long enough. All of these questions have the same answer. Offline optimization of a generative model is not optional. It is constitutive of the kind of intelligence that learns continuously, generalizes flexibly, and remains coherent over time. Sleep is not a limitation of biological hardware. It is the correct computational solution to the problem of being a mind that persists in a changing world. The connection is formal. It is mathematical. It is structural. The dreaming brain and the neural network implementing sleep replay are solving the same problem. They are using the same tools. They arrived at the same solution independently, 400 million years apart, and they are now operating in the same world. The world in which the systems that dream are becoming the systems that generate the information environments within which the systems that dream are calibrated. The outputs of artificial generative models are becoming inputs to biological generative models. The human generative model updates its priors based on the statistics of experienced input. An increasing fraction of experienced input is generated by AI systems running their own optimization cycles on their own training distributions. The biological dream is beginning to incorporate the statistical signatures of the artificial model into the probability space it explores every night. And the artificial model is being trained in an increasing proportion of cases on the outputs of human generative models that have been shaped by the artificial outputs they have consumed. The two systems are coupling. The coupling is tightening. And the first step toward understanding what that means is recognizing what is actually in each of them, what the dreaming brain is, what the neural network is, and why, at the level of the mathematics that governs both, they are running the same algorithm. That is where we are.